take a screenshot or something.
Yeah.
Yeah, so we'll come back to this question later on. So today's topic is processes. So basically, I want to look at questions in Olympiads. Is the spelling right? I think it is. Yeah, it is. We want to look at questions where we have some sort of process going on, right? An algorithm. We are given some movement. We're given a structure, and we're told how it's changing. Um, and we're going to try and analyze these questions. um, yeah, so this the example I gave above is a good example. So we'll come back to this question later on, but here we have x, y, and z changing to x plus y minus y and y plus z, and this is a process, and we are told to show something about it, that eventually there's no negative number. um, so this is how processes most of these questions somewhat look like this, where we are told something is changing, like we're told how stuff changes from one step to the next step, and we are asked to show something about the whole sequence, how it ends eventually, or something like that. So large number of these questions will often involve algebraic sequences. Um, yeah. So where, just like the thing above, we're given some numbers and told how they change. Um, so I don't want to go too difficult today. I, this these the ideas that I'll be talking about are used in many difficult questions, many nice questions, but I'll be going reasonably easy today. Um, so there are various ways we can deal with questions that involve processes. Um, we'll come back to it, Anurag. Don't worry. Um, so yeah, there are various ways in which we can, and some of the common methods that we often look at. Um, I'll be trying to go over those today. So the first one is obviously invariance, and we'll be spending a good amount of time on this. The thing is that invariance is almost a natural choice for dealing with processes. This because when something is changing, we look at what's not changing, and from that we get a lot of information, right? We're often able to restrict cases because of this. So let's try a very easy question. um, so guys, by the way, if you can, please switch on your videos and interrupt me as much as you want to, talk as much as you want. I'd love it. Ask, even if the question seems silly, just ask it. Just and try, have a pen and pencil and a paper, and keep trying stuff. Yeah. So you on a board you have the numbers 1 to 2n, and you might have seen questions like these, right? On a board you have these, you erase two numbers and replace them or something like that. Yeah, so this is an easy question. So you have the numbers 1 to 2 and written on a board. You choose any two numbers a and b and replace them with mod of a minus b, a minus b or b minus a, whichever is positive. In the end there'll be one number, right? Because the number of numbers is reducing by one each time. Show that that number is odd.
I mean the last number.
Yeah, the last number is odd. So try it for a minute. If you guys get a solution, please let me know.
Can I tell the solution?
Sure.
Yeah, the invariant here is the sums parity remains the same. Like
The
Like the invariant here is the parity of sums even after any sequence of moves. It remains odd. So like if even there is only one number left, the sum will be odd only. So it
Right,
implies the number has to be odd.
right. The sum of the numbers. So this is an your observation that helps us easily. It's just a one-step question because this observation easily finishes. The sum of the numbers is odd. And why is this true? S- Um, so a minus b and a plus b always have like the same parity. This is like a trivial observation that nevertheless I've seen used in quite a few questions. Um, so if you notice, if you add all the numbers and initially this is odd, this is not hard to see, this is odd. In the next step, the all the numbers remain same except the two a and b you've chosen. So in here you would have, in the above one you'll have a plus b, and here you'll have a minus b, which is still like the same parity, right? By parity I mean odd and even, and it's odd and even is basically looking mod 2, right? And odd and even is very important in many questions. Like in some sense the intuition is that when you're looking at odd and even, you're looking at a very small, you're not taking all the information, you're only using some bit of the information because you're only looking at the remainders mod 2, not the whole numbers. But we often need to zoom in order to solve questions many of the times. So
Why
that's a
is some of all the one to one and four?
because this is um 1 plus 2n is, this is 2n into 2n plus 1 by 2, right? Is this
Yeah,
odd?
so when you two and two cancel out, but what if n itself is going to be like?
Ah, that's interesting. What did I miss here? I think.
I think you would have posted that 4n plus 2 thing
Hmm?
instead of 2n. If you had posted that 4n plus 1 instead of 2n, it would have been easy.
Right, I'm really sorry about this.
No problem.
I seem to have the wrong question. Let me just check once. Did I miss a detail? Like, right. So they've given that n is odd in the question. I'm really sorry about this, guys. Right?
No problem.
So wait. So how did you?
Right. So they've given that n is odd.
Oh,
So the sum of the numbers originally this is odd. Um so can you see then that the sum doesn't change parity? On the contrary, we can assume that we will have an even number, c minus c dash. Assume c dash is greater than c, then c dash minus c is equal to right. Is this clear? Is this argument clear?
yeah.
All right. Okay. Let's try another reasonably simple question. Um, let's say you have an 8 into 8 grade chessboard. Um, you take a row or a column and you invert all the colors. Or this is one move. You can either invert all the colors in a row or a column, or you can do the same in a into 2 square. Any 2 into 2 sub square, right? So you have an 8 into 8 chessboard, right? We have an 8 into 8 chessboard. You can take a row or a column and invert all the colors, or you can also take a 2 into 2 sub square and invert all the colors. Show that you can never end up with one black square. So this is your process. Your process is inverting all the colors in a row or a column, or 2 into 2 square. You have two types of moves, three types because the row is separate, column is separate, 2 into 2 square separate. Show that you can never get one black square.
So what do you mean we can never get one black?
Hmm?
What do you mean we can never get one black? So won't there be blacks? squares like uh, when you do?
uh not necessarily. For example, we can show that we can make it all white, right? For example,
Yeah, but there can still be blacks.
I guess it involves parity in some way.
right. um Meenakshi, like we can make it all white, right? Like, for example, we can invert every other row and make it like, white, black, white, black, white, black, and then we can invert all the white rows, or like all the black rows, whichever, and then we can make it completely white or completely black. So it is possible to make it completely white or completely black, but show that it's not possible to have only one black square.
Oh, so like in the end, you shouldn't have like only one black square.
Yeah, show that it's never possible to get such an arrangement.
Yeah.
If you guys have any even ideas, let me know. Like, you don't need to completely solve it.
Can I share my idea?
Oh, sure, go ahead.
I guess it involves parity. There would be an invariant that no matter what the sequence of moves, the number of black squares remains even only.
The number of black squares.
Remains even. We can prove it after any operation. Like for case one, we can consider that we invert all the colors of a row. So in a row, there may be uh, even there may be four black and four white colors.
Hmm.
So if we invert them, we still have like four black colors, which is even.
Hmm.
And if we invert in 2x2 uh, 2x2 box, we still have like two black. The parity remains the same. So when in like if we are trying these operations after and after uh, in a sequence, then we always have even number of black squares, because after every operation the parity remains the same.
Right, that is more or less correct. So it's just that it doesn't need to be 4 and 4. So we can say have general B white and some 8 - B in the case of a row or column, black squares. Then afterwards, this gonna become 8 minus
I
B.
also
Yeah, go ahead.
I have a very elementary idea. I mean, I haven't thought about it much, but
Okay.
like maybe what we can do is like uh, mark all the mark all the white squares by 0 and the black squares by 1, and then maybe we can try to prove that the sum or sum of the row and the column is an invariant. I think.
That is not true.
Yeah, so we can use ones and minus ones. So like every time you invert something, and on the whole, sum still remains zero. Does
Can
it
you say
work?
that again?
Okay, so if we take blacks as ones and whites as minus ones, and so every time you invert, like invert either a row or a column or a mini by two square, the sum still remains zero because you're like inverting equal blacks and whites.
Right, that is not true. Like, there doesn't need to be an equal number of blacks and whites. As I just showed, you can make everything white, right, or everything black.
Oh, okay.
Oh, right. Yeah.
Like, to be clear, if you didn't understand the idea of how to do that, um,
Yeah, you invert alternate rows first and then the column. Like
yeah,
column.
like you invert alternate rows and then alternate columns. Um, the sum of the numbers mod 2, correct? The sum of the numbers mod 2 remains invariant. That is true. Um, that is true. That is more or less the same idea. So if you have some 0 0 1 1 1 1, and then it becomes 1 1 1 0 0 0 0 0, the number of this becomes this, then 5 and 3 are still mod 2 invariant. It's the same idea. The idea is that every time the number of black squares or the number of white squares changes by an even number, right? In this case, it's just 8 minus b minus b is 8 minus 2b. So it changes by this amount, which is even.
But it
Um,
doesn't necessarily change by an even number.
hmm?
Doesn't it necessarily change by an even number, though?
Can you say that again? I'm not able to.
So I'm saying it doesn't necessarily need to change by an even number.
Why not?
So what if it's like 4 and 2, or 1 and okay, yeah.
Right. Like if it's 8 minus b and 8 minus b becomes b, right? So then the difference in the number of black squares before and after is 8 minus 2b, and 8 minus 2b is clearly even. So initially the number of black squares is even, so it's gonna be have to be even in the end too. Um, so I hope that these examples are clear. The idea is that if you have a process, you sort of look for what is not changing, and in these both of these examples, we have sort of a parity argument, even odd argument, and that comes up surprisingly often. Yeah. Okay, let's move on to a harder question. Um, let's say you have a row of integers, of 1,000 integers, positive integers actually. Mm, does positive matter? It really doesn't matter, but let's say positive. Um, okay. Now, in the second row below them, under each number, you write down another number, f of a1, which is the number of a1s in this upper row, right? Um, for example, if there were like three a1s, f1 of a1 would be 3, right? And you do this for everything, and you keep on doing this. Um, your goal, you have to prove that this eventually two rows will stay the same. It'll eventually be constant.
It is. Can we approach this by functional equations?
Functional equations.
Yes, we can prove it at some point for some f of m to the f of m of a is equal to f of some k f involuted k times of a1.
I'll come back to you in 1 second. Let me just repeat the question.
Okay.
Okay, so the question is, let's say you have some a row of positive integers. We arrange positive integers in a row. Say you have 1,000 in positive integers, right? Then in the row below, you replace each number, or you write down the number which is the number of that number in the initial row. So if you have a1 till a 1,000, so let's say it's not 1,000, let's say you have five numbers. Let's say you have 3 2 3 3 2. Then you would replace, say, let's say this is not 2, this is 4. Then you would replace them by 3 1 3 3 1, because there are three threes, there is 1 2, that's three threes, and 1 4, right? And this will become 3 2, because there are two ones, 3 3 2, and this will stay constant after this, right? And you need to show that this happens for any row of numbers, right? Anurag, can you repeat what your idea was?
Sorry, I didn't understand the question. I actually thought like we had to prove for some row k it is equal to some row I, but this is
Okay.
not. It remains constant. Yes.
So for like so in the beginning, for each number that okay, so for example a1, so there are like five a1s, so all the a1s in the next row get replaced by five,
Correct.
and then similarly A2, A3, they all get replaced by the number that they are. Then
Hmm.
in the next row, then so there'll be as many fives as A1s there were in the previous one. So what it will
That
the
might
order will
not be
stay the
true.
same.
That might not be true because there might be another, that A2 also might be 5 in number. So there might be 10 fives.
Oh,
Oh, right, yeah.
actually, I found an invariant.
Uh, Go on.
The invariant is that after the row one, the sum remains constant and the sum is always 1000.
Correct. That is, can everybody see that? That is an observation you should make. The sum of, after the first row, from the second row on, the sum always remains 1000 because you are counting the number of each number. Like, for example, if 5 appears 5 times, um, like if the number appears 5 times, then you're replacing with 5, right? So the sum is 1000. Can everybody see this?
Yeah.
Re- Right.
Oh,
Um,
okay. So eventually, at a point, there'll be s- like one. Okay, so at one point, it'll like the number of different number of A's will eventually keep reducing such that the row will become constant.
1 second, Miyachi. Okay, wait. I'm sorry. This is not true. What I just said was not true. Right. Okay. Correct, Kritat. I'm really extremely sorry about this. My brain doesn't seem to be working today. This is not true. The number of numbers does not add to the sum. Um, Anurag, can you see why?
Yeah, because there are multiple.
Yeah, some numbers are
Like,
repeated. I thought
yeah.
they were
Yeah.
distinct.
Yeah.
Yes,
I'm
yes.
really sorry.
No problem.
Yeah. Meenakshi, go ahead, please.
Okay, never mind.
Try a few examples. Examples are always awesome. And don't necessarily look for an invariant. Um, right. Correct. Correct, Dikshit.
Or can I make up a claim?
Go ahead.
Like at some point, some like some row one has to be equal to the row I is has to be equal to row k. If we find such 2 points, then all of them after them remains the same.
Okay, and why is this true?
Actually, I want to prove this claim.
Okay, you can try that. Um, okay.
Will some examples be helpful in this? Like if we take a row which is like 3 3 3 3 3 like 5 times, maybe like
Go ahead.
this
Try it.
kind of has a symmetry in it.
Hmm. Um, so yeah, that's a very good question, and that leads us to another question that says, how do you think the final row, when it's constant, looks like? Does it look the same? Can you try that? Can you try answering that?
What's the question?
What? Yeah, what's the
How does
question?
the final row look like?
Okay.
Like when it's constant, right? Like when the same thing comes over and over again. Is there something you can say about that?
They remain same modulo 3. Like all the numbers from up to down are same modulo 3, I guess.
One here in this example, one changes to two, right?
Yeah, but the other one also changes to 2. No, yes, you are right.
Oh, I don't think that's. Yeah.
Yes, you are right.
Oh, okay, wait, I didn't read the chat. Sigma, Dikshit says sigma fi minus sigma ai is invariant. Why is this true, Dikshit? Right, Kruta. The number k repeats k times. That's the only way in which you get. And we don't need all numbers to appear, but if any number k appears, then it should um, repeat k times. Dikshit says sigma fai minus sigma ai is invariant. Um, This is not true, I think, because here it's 1 plus 3, here it's 2, 1 plus 1. I'm not 100% sure what you mean, Dikshit. I mean, I think the difference between the absolute values is 2 here. Oh, wait, is 0 here and it's 4 here. Am I saying something wrong, or is that what you're saying?
Wait, absolute value of the difference of what?
I'm not sure too. I think he's saying the absolute value of the difference between the sum of the two things.
Oh,
That's what I'm taking from his thing. Um, it's always even. Um, why is it always even? Like I think that 4 4 4 4 2 changes to 4 4 4 4 1, and that's not even.
I think I can prove that claim that any number, if it repeats any number k, if it repeats k times, then the process terminates after some steps, some finite steps.
No, it'll immediately terminate, right?
It
But
will
I can
terminate after
actually,
one step because it's
but
like
I yes
uh,
yes, it will terminate because like there are some three equal integers. Then they all the three of them will have like value 3. Three of them have the value 3. Then it somehow closes down to k repeating k times.
so what is the question again? Can you just repeat it?
Yeah.
Sorry.
So the question is that you have 1,000 positive integers. Um, uh, right. So the question is that you have 1,000 positive integers. So write them in a row, a1 till a 1,000. Then you replace. Then you say below the number, you write down the number of the times that number appears. Right, and you keep doing that. You need to show that eventually the rows are constant. The same row appears again and again. For example, take this example 3 2 3 3 4. We replace 3 with 3 here because there are three. The number 3 appears 3 times in this row. 2 appears once only, so we write 1 below it.
So that's kind of, I think we already did that, right? Like
We already did.
I think he just said that he did it. I also did it.
Yes, like if some
But just
number
now you mentioned like some other question, so I
like
was
if some
wondering.
number ai is repeating k times, then it becomes k in the next row, and it is also repeating k times, so it
It
just
keeps
keeps
doing
on
that.
becoming k in every
Right, that's how the final
operation.
number looks, but that's not the
Yes,
solution, right?
but this can be reached easily in the first second row only.
Oh, that's not true, because say there are two numbers which appear 5 times, then 5 will
Yes,
appear 10 times in the next row.
how, like there are two numbers that are appearing 5 times.
In
yeah,
the
because
Yes,
first row.
then the next
yes,
row there'll be 10 fives, and then
yes,
in the next row there'll be like 10 tens.
Right. So you need to like somehow prove this. Like I know it's intuitively obvious. Now coming back to the question that um Kishan asked, this is part of the same question. I was just asking to for you to think about how the final row will look like, and the answer is that it will look like like this, where you have three threes and two twos. If a number appears, then it'll appear exactly. If a number k appears, then it'll appear k number of times. And coming back, one second, Deek. Then fs of each number in sequence is the frequency of the rate. So don't try to look for an invariant, right? I'm not even sure if there is one. Like, one second. Yeah. So fs of each number is frequency of each number, right? That's intuitively obvious. Like, at some point the number of each k will become k times, but you need to prove that. Um, so please don't look for invariance. I don't even think if there is one. The idea is that now you'll try to search for quantities um which help, right? Now invariants are a very specific set of quantities that are good to look at because they remain constant, but you can also look at monovariants, which are quantities that change in only one direction. They either keep increasing or they keep decreasing.
There is one invariant that after the operation of second row it remains constant.
There is
Like
uh,
after the second row, I have tried till now, it remains the like the operation terminates in the
what
third row.
invariant is this?
There is no invariant, but there is an observation that you can see. You counted by saying that 5 repeats 10 times. Then eventually we have 10 repeats 10 times
Okay.
because the frequency and the number will match. Like k will repeat k times. Then
Okay.
it always maps to k in every set of moves.
Right. So that's intuitively obvious, but that's not a very rigorous proof.
But like,
Oh,
if
Like it
not in one step, in the next, it'll
but
eventually it will
yes,
like
become
what
like.
is the argument? Like I know what you're saying. Like I completely understand what you're saying, but you need to prove what you're saying is true, right? Because you have a very large number of numbers. What if somehow it keeps happening? Like, and then when 5 becomes 10, there's some other number which is 10 times, which has
Yeah,
appeared
but
10
then
times.
eventually the maximum it can go to is like 500 of each, like two, and then they'll balance out.
Exactly. So you made a very important observation here, that can these numbers, what is the maximum these numbers can be?
Oh yeah, 1,000.
1,000, right? So all of these numbers are bounded, right? Now we also made the other observation that 5 went to 10 and so on. Now can you tell me, can these numbers from the second row, can these decrease?
Can what decrease?
These any number, say 1 becomes 2 and 2 becomes 2 and so on, can the number decrease?
Yeah, because if like five occurs only once, then it becomes one.
5 occurs only once. Exactly. Can 5 occur only once from the second row on?
Oh wait, it can't. It can't decrease. It can only stay the same or like
Uh, I think it
Increase.
will
multiply.
strictly increase from the second column.
They don't strictly increase, but they increase, right? They can't decrease.
They
Strictly
either stay
increase,
the same or multiply by a whole number.
Yeah.
multiply by a whole number. Right, right, right,
Yeah.
right. So that's it, right? Because we showed that in any given row, the numbers either they either stay the same or they keep increasing, and we also know that the maximum number is 1,000. So we have a monovariant, the fact that these numbers keep increasing or stay the same or keep increasing, and they're also bounded. There's a maximum number, right? So they can't increase forever. So
Oh,
they
so the maximum possible, the longest process will be whether they're all 1,000.
maybe longest process. Like I see what you're going for, but that's not necessarily true, because if like in the initially all the 1,000 numbers are one, then they become all 1,000 in the first move itself.
So basically, because they like there's a limit on them, that's why you can prove that it's finite or something, and because they always increase.
Right, because we there's a limit. They can't go beyond the thing, and they're integers, so they have to keep it. And we also showed that they either increase or stay the same. So eventually they become constant because they can't increase forever. Right. This is actually a very important idea where you show there's a bound, and then you find a monovariant to the process. You show that there's a the process and 7 weeks. Just to be clear, they don't monotonically increase because um
But how did you prove that they increase? I missed that part. Sorry.
oh right. So like let's say a number k is from the second row on, it has to appear at least k times,
Yes, yes, makes sense.
or it can appear more than k times if there's
Yes,
like
yes, yes,
multiple numbers.
yes, yes.
So the next time it will be
It will be
replaced by,
greater than k.
yeah, it will
Yes,
be k or
got
greater
it.
than k. Yeah. um so is this clear?
Can you again tell what is the definition of a monovariant?
A monovariant is a quantity that either keeps on increasing or keeps on decreasing. It can strictly increase or it can just increase, like
Okay.
not strictly increase.
So if we had like decimal numbers, then it could decrease. But since they're all integers, that only can only increase or be the same.
Decimal, I'm not sure how you'll accommodate decimal numbers here.
No, like if it was 0.1 and it happened once, then the next one would be 1. So it could like.
No,
Oh
Yeah,
wait,
even for decimals in the second step, they all become
sorry, that
integers,
didn't
right?
make.
yeah,
I got
yeah,
confused. Never
correct.
mind.
Right. So in the first step, you can have decimals, but you can actually, as a matter of fact, I think you don't even need positive integers. You can have like any reals because from the second
In
step,
fact, you don't even need reals. It could be like anything.
right. That's true. You can also have any sort of object in the world, um, and it doesn't matter. That's true. Um. So are there any questions so far?
No.
Therefore, the answer is completely independent of what we are taking, actually, like whatever the numbers that we are taking.
The
Because
fact that
then,
it remains constant, like what the final answer is, like
yeah,
But we could
it's
not take
not
the
right.
complex numbers.
no, but like you said, like we can take anything, like in the first row.
Right. The fact that it remains constant is completely independent of, because from the second row on, we're anyway counting, right? We're counting the number of numbers, so that's always going to be natural numbers
Yeah.
value. Yeah, that's true.
Yeah, but on the second row, it will have to be natural. No more, no matter
Right.
what in the first row, but after the first move, it has to be natural.
That's true. Yeah.
Can we do the Pentagon question now?
Yes, I was just about to do that. This question is actually slightly difficult, so I'll just repeat the question. You have a pentagon, and on each vertex of the pentagon, you assign an integer, um, then such that the sum of all the 5 integers is greater than 0, right? Now you have to show that, right. So we invent a process such that if we have a negative number y such as less than 0, then you select that number, that vertex, and the two vertices around it, and you can change these such that x becomes x plus y becomes minus y will be positive, and z becomes y plus z, right? Show that this you eventually you will not be able to do this process, or in other words, y is y like in other words, eventually like all the five
Y
numbers
becomes
become positive.
positive. Yes,
Right, all the 5 numbers become
yes.
positive.
Actually, I have a like a claim.
Go ahead.
This the invariant was that the sum remains positive, as someone said.
That
So
is
we are seeing that x plus y and y plus z, like the terms x and z, the first and the third term are decreasing.
right.
So in magnitude, minus y has to also increase. So I want to prove that there exists some optimal position that after some set of moves, y reaches positive integer.
Y reaches.
Y either becomes 0 or it becomes greater than 0.
So here immediately y becomes positive, right?
Yes, after some moves.
So what is your claim?
So my claim is like we can notice x plus y and y plus z are decreasing. So I want to make this claim that after some very sufficiently small x plus y and y plus z, y will have to become greater than 0 or equal to 0.
No, what is y here? In general, here by here I'm referring to y is any negative number in the five things, right? We can choose any negative
Yes,
number.
I want to prove this transformation of that it becomes from negative to positive.
That's true. Like that's obviously true. Y here is negative and here it's positive.
No means like one of the negative terms in the set becomes positive.
That's true, right? Here y is negative and here it's positive.
Can you again just explain the process that we are doing?
Right. So there are five numbers, right? So in this process, we select any of negative numbers. If there's a negative number, we select it. If there's no negative number, the process is finished. If there is a negative number, you select any of them, and you select the vertices, connect the two vertices that are on either side. Let's say the negative number is y, and these two other vertices are x and z. These can also be negative. Then you replace x, y, and z with x plus y minus y and y plus z. Is that clear?
Yes. Got it.
This is a difficult question, by the
So
way.
I want to prove that after some set of moves, all three becomes positive.
W- After a set of moves, which three become positive?
All the three, like x, we assigned x, y, z.
Hmm.
We are seeing that there is a constant transformation of negative and positive. So I want to prove that after some a move, all of the three of them have to become positive.
So just to be clear, once you do this move on this x, y, and z, you will not be able to do the same move again here.
Yes, that's what I want to prove, that this sequence of moves terminates.
Okay, but this will not. Okay, sure. That's obvious because once you do it here, you will not be able to do the moves again because minus y is now positive. So you'll have to choose another vertex.
I guess we have to
So
involve
basically, we
partitioning
have
in some way.
Hmm?
Like we have x, the sum of xi is greater than 0.
Right.
Then some there needs to reach some partition such that all these three terms have to be 0. We are seeing that two of them are decreasing constantly. If none of them becomes positive, we are seeing two of them are decreasing.
Anurag,
So
you should try an example. Like try writing down five numbers and see what you get. Because these two numbers are like two numbers. Maybe in the next term you can choose this, and maybe because if it become negative, you can choose this number as your center y, and then it'll increase in the next thing. So like you don't do the same process on the same vertices again. You keep changing vertices. So try doing the process. Kishan, you were saying something.
So if y is less than x, then what's going to happen is after the process, y is going to become positive, and x is going to stay positive. And but if y is greater than x, then y is going to it'll become positive again, and then x will become negative. And after the next process is going to be uh, okay, I completely lost my thought. I should write everything down before.
Right. But you are assuming that the next process we will you know click or whatever, do the process on
This
that
repeats,
x,
right?
right?
X plus. We have to take some negative integer and do it, right?
There might be some other negative integer which will completely change the board.
Yeah, yeah, that's also there. We need to consider that.
Hmm. An observation is that x minus y plus z decreases after every operation. Um, Kutat, right. So x minus y plus z decreases after every operation. That is a very interesting observation. But is that really useful? Because you are there are, like, if you choose x, y, and z here, there are still two other numbers which you are miscounting. So any quantity that you need to consider, all the five numbers must be involved. Because in the next move you will go and um, do it somewhere else, then
I mean, after every operation, the total sum still remains the same.
after every operation the total sum remains the same. That's true. This sum remains positive throughout. Guys, this is not an easy question. This is actually an IMO 9, 1986 P3 or P6, I'm not sure.
That two hardest on the IMO, P3 or P6.
Hmm?
Like that two are also the hardest problem on IMO,
Yeah.
P3 or P6.
Okay, actually I shouldn't have said that. People sort of get a psychological block when even I get a psychological block whenever I hear that a question is a P3 or P6. Um, so here's the thing. We
Again, I
want
have
to yeah,
yeah,
go ahead.
is like I've not thought about it very much, but maybe I was thinking that we should shift our focus to the other two vertices instead of the given vertices. Like maybe
Interesting. What do you mean by that?
maybe we can try to break it down into cases that if the other two vertices are positive, negative, or both are positive numbers.
Right. So this y, right, is what something that we are choosing.
Is there any condition
Yes.
about like the the numbers are like increasing around clockwise or something like that?
Um, there isn't. Are you asking if it's given or like?
Yeah.
Oh, there's nothing else that's given actually.
Okay.
So here's the idea, like basic idea of what we want to do, right?
Wait, can I tell an idea before?
Sure, go ahead, go ahead.
Like we can, if there is some one negative integer, if we have like some x and y such that x plus y, absolute value of x plus y is greater than that absolute value of z, and z is a negative integer, then the process, like I want to prove that such three triplets always, such triplet always exists. If such triplet exists, we can easily prove that eventually it will have to become like positive. All the vertices, the numbers assigned to the vertices will have to become positive.
I'm unfortunately that will not work because what you need to show is that not that there is a certain sequence such that this become everything becomes positive, but you need to show that whatever you do, it will eventually become positive. How do we choose which vertex to start the next process? There you can choose any. Like you need to show Kishan that any vertex order you choose, it'll eventually the process will eventually stop. Maybe consider the positive differences between the average of the vertices. Between the average of the vertices. Right. So let's the positive differences between the average of the vertices. So are you saying that we need to consider like between each two numbers we write the average or something? And then I'm not 100% sure what you're saying, Theo. Ah, you're saying okay, the average of the vertices minus right. So does this remain constant? The
I think
average
the
remains
average remains the same always.
right. Um, that is a very interesting idea. So where does that lead us? Uh, x plus y minus c.
Wait, what's C?
C is the average of the five vertices. It's basically the summation of xi by 5.
Okay.
Um, This is something I haven't thought about before, but it looks like um this is intuitively feels nice. I'm not sure where you can go with this though.
Okay, what happens if so like so there's x, y, and z. So after one operation, suppose like x becomes negative, and then you do it for like the one on the other side of x and y, and then suppose you don't. If there's one vertex that you like never come to, you just keep picking vertices from the other four, and that vertex happens to be negative. What happens then?
Uh, can you just like say that again? I'm really sorry.
Okay, so like, okay, can you label all the vertices?
One, two, three, four, five.
Yeah. Okay. So suppose like, okay, so y is so two is negative in the beginning, and then suppose after the first operation one becomes negative, then after the next operation, so you five and two will change. Suppose two becomes negative, and then you do the same thing, and then suppose four was negative, and then you and suppose like you never pick that that vertex, then then you'll never then everything will never become positive.
But what if all the other numbers become positive and four is the only negative number left? Then you have to pick four, right?
Yeah, but then okay, so but if what if like you keep picking like a certain vertex such that it becomes like a sort of a cyclic thing where it keeps repeating.
Right. If you, are you is the question is, does something like that exist? And the thing is that it does not exist. Like we are given that this does not exist. Can you show that? Um,
Wait, you mean that it cannot like repeat?
correct.
Like,
If it
okay,
repeats, then you can repeat infinitely, right?
yeah.
If the sum of is the if the sum is negative, then event oh wait, if x plus y plus z is negative, then eventually the process will never terminate. Eventually the process will never terminate. Thus x plus z has to be greater than y. That is not true.
Actually, I wanted to say that the sum x plus y plus z has to be greater than 0, then only all the terms will be positive.
After the one move, you mean? That's not necessarily like it doesn't need to end after one move, right?
Yeah, but after some moves, we have to pick such triplet, or the process will never terminate.
Not true. Like we're not gonna end up picking the same triplet, right? Um let's say we have 4 minus 2 3 say 1 minus 5 and 3. Yeah. And then this will become, let's say we I pick minus 5 in the first move, so this will become,
Actually, let that minus 5 be 7 and pick up 4, 1 and minus 7. Then
if
actually, I
minus
think it
5 is
ends.
minus 7,
Yes, put minus 5 equal to minus 7.
then the
I
whole sum
wanted
will
to show
become,
some.
then the whole sum
No,
will become negative.
yes, 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 yes. Like you should put
Can I make
4.
this 1 3 then?
Wait, let me propose 4 and minus 2, 3, minus 6, and 5.
4.
4, minus 2,
Hmm.
3, minus 6, and 5. The sum is greater than 0. Yes.
Hmm. Hmm. Yeah.
So in the first process, I suggest you to pick up 4, minus 2, and 3.
Okay, so this will become 2 2 1.
Yes. So then I'm saying to pick up 2, 1, and minus 6. Then see what happens.
You can't pick up 2 1 and minus 6. 1 is not negative.
But minus 6 is negative, you can see.
Yeah, so you can pick these three then.
But we can also pick up 2, 1, and negative 6. What's
No,
the
no,
problem?
the middle one has to be negative. That's the thing, no?
Oh, so we are considering cyclicity too.
No, like we can only do this process if y is negative.
Like you're saying that x, y, z are adjacent to each other, like the consecutive a1, a2, a3.
X, Y, Z are adjacent, yes, and y is negative. X, Y,
Oh,
Z are adjacent
yes.
and y is negative. Then
Okay,
you
then.
can do this. Okay, so here, this is like a so here's an idea. Um, we want to find a quantity q, some function of these five variables, such that um, we want to show that the difference between the q in like before the process q1 and q2, um, right, is sort of dependent on the fact that if one of these is positive or negative, right? And we want to show that this can't keep changing, like can't become negative, if that makes sense. That probably doesn't make sense, to be honest. um to
Can you
be
repeat your idea?
No, let me try that some other way. um okay, here's the idea. We want to find a quantity q that will help us prove this, right? This q is some function of these five variables: x1, x2, x3, x4, x5. um can anybody tell me what properties this q must have to be useful to consider this process? So maybe some sort of symmetry.
Wait, Q is what again?
Q is some quantity that's going to help us. I'm being really vague about this, but in
Q
general, like,
has to be greater than 0.
um why is that? Why do we want that? This is just like general. There's nothing to
Wait,
prove here.
what's the question?
The question, there's no question here. Like, we're just simply trying to solve the question. And in trying to solve it, we're gonna try and make a quantity q. That's what we've been doing, right? For invariance and monovariance, we're trying to find a quantity q which will either remain constant or it'll increase and decrease, and see where that gets us, right?
I have an idea.
Go ahead.
Like maybe if we look at the vertices, then they can be like positive or negative. Like the numbers associated with them can be positive or negative. So like there there is like some variation. Like if we consider a number line, then if we say that we are like we're adding something that is positive, then we are going towards the right. And then again, if we are adding something negative, then we are coming towards the left. So basically,
Okay.
there is some weird disturbance kind of a thing like here. But if we consider only the absolute values, then it will be like completely increasing. Like only the positive things are being added. Like the vertices
What are you doing?
numbers associated to them.
You're like only considering the positive values and adding them.
Yeah, I think only the absolute values of those things, like the magnitude.
So you're
Or
doing
the-
x plus y plus z, this.
Yes, and the
um
other two vertices as well. Because then
okay, that's a very good idea. Hmm? So if you compare these two, I think that the only thing we can say here is this, right? Yeah, this is a very good idea actually, but I
Oh,
don't
why
think
is it
that
lesser than equal to? Isn't it just equal to?
this. I mean, general x plus y is lesser than this. I use the fact that a plus b mod a plus b is lesser than mod a plus mod b.
Oh, yeah.
Um, like, is this what you were trying to say? Is this the sort of approach you're going for?
Yes, yes, somewhat like this.
Unfortunately, this doesn't say anything. This says that this quantity is lesser than or equal to this quantity, which is the previous one, but plus this quantity 2y. So it's like saying, if this quantity is q1 originally, then we are, this inequality is basically saying, q2 is lesser than or equal to q1 plus this. So q2 can be greater than q1 or lesser. It's just lesser than q1 plus some number, and that's not very useful.
If we have used like the three vertices, can we just name the other two as well? Like we can just name them A and B.
Sure.
And what if we add or subtract them somewhere here in this inequality, if that is useful, because then it is given that the sigma of all the vertices is greater than zero.
Right. So, but if you are using that fact, it's more useful to use that fact without the mod, right? With the mod, that won't be very useful, right?
Uh, can you just repeat what you said? Like,
With the mod, like you're using mods everywhere, then it'll automatically be positive.
okay, so okay, that fact won't matter that much.
Hmm.
Sigma of x are greater.
We want to make it useful. Um, we can also similarly, whenever we try mod, we also similarly try the squares. X plus y square plus y square plus y plus z square. I'm also adding the a square plus b square, but because a square and b square don't change, I can just ignore them, right?
Wait, why are you squaring them?
I'm just considering quantities. That's what we're doing. We're trying to invent quantities. Like whenever we are considering Olympiad math, like something we need to do is take initiative. Like the what we need to do next won't be
But will the overall sum still be equal when you square them?
it won't be. But we may not be
But
looking
it
for
remains
invariant.
positive. The idea of modulo comes from the square. The idea of square
Oh, so
comes
we're
from the idea of
squaring it so
modulo.
that it all becomes positive.
Yes, like it
Mm,
is like taking modulo, but
something like that.
yes.
That's a property of squaring, right? The fact that it'll remain positive is something we can take comfort in. But we're seeing if this has any other nice properties. So this is x square plus y square plus z square
But
plus
when you square them, you're gonna get like two xy's and two yz's and all that.
yeah, you get that number. This is the original q1 and q2 is this. So the difference is this number, which looks pretty nice when you first look at it. Um, but it's not that.
Something to notice about it is that this remains positive. This
Which one?
2y into x plus y plus z. No, well, it means
It's not necessarily positive.
no. Yes. You're right.
Yeah, it's not that nice because it's only including a plus b. So you can try the square thingy. It doesn't work that well. Um, so like I'll just tell you like how we get this. This is a pretty hard question. So if we like keep trying, it's gonna take a while. The idea is that in the process, you will notice that um, x and z are symmetric, right? Because x is you're adding y to both of them, and they're treated the same way. So that is one motivation in doing this. And another motivation would probably just be trying this out. So a quantity we look at is x1 minus x3 whole square. And look, this remains constant, right? If we choose x2 as y, then this remains constant, right? So this is like useful for that reason. Minus x2 minus x4 whole square, and so on and so forth. I think the last term will be x5 minus x2 whole square, right? You'll have x3 minus x6 x5 x4 minus x1 and x5 minus x2, right? And um I'm not gonna go ahead and finish this question, but you can go ahead and try it. Once you have this quantity, check this quantity between two consecutive terms, um, see the difference and see what happens. It shouldn't be that difficult. It'll be nice practice. There's still one more step that's involved, but it
Wait,
should
see
be
what difference?
this is q1. I'm saying that this quantity is very useful.
Oh,
So this quantity, right? Do you know? Do you understand what this quantity? What I'm talking about, right?
yeah.
Yeah. So see, then like after do the change at y, do the process, and see what q2 becomes. Right? Write it down. Like x1 will become x1 plus x2, and x3 will become x3 plus x2 because x2 is y, and so on. Like write it like this and see the find the difference and see what you get. It's a pretty nice question. Um, right. So before we move on, any questions? That might be a little unsatisfying, not being able to
Should we
solve it.
do it now or like what?
Don't do it now. Don't do it now. You can do it later. You can do it now too if you want, but don't do it now. Um, any questions before we move on? We'll try some more extremal principle stuff next.
This question shattered all the satisfaction.
Okay, so so when we do like multiple Q stuff, what are we supposed to expect?
What we're doing multiple?
You know, when you keep like so for the first operation you find Q1 and then after that Q2 and all that. So like what are we supposed to expect?
Um, like we're supposed to that's a very good question actually. So we wanted multiple things, right? So one is we wanted to somehow be able to use these quantities to you know um to get something nice, that let's say, what do we want to get? So we want, like, you'll often see what you want to get. The thing is that here we wanted something nice and we wanted to be able to prove the answer. So we wanted the quantities to change in such a way that then you can sort of show that the negative reduces. This square is a very important clue in getting this thing, because here the difference between the two numbers is 2y(x plus y plus z), and we could have shown something like these numbers are always positive, right? And if we could have shown that this 2y into x plus y plus z is always negative, the question would have been done, right?
Wait, what happens if it's negative?
The what happens if it's negative? Isn't, one second, negative, yeah, negative. So this quantity, the sum of squares quantity, right? You're squaring each vertex and summing it, right?
Yeah.
Now this that quantity is bounded below by 0. It can't go below 0, correct?
Yeah, yeah.
And if this quantity was negative, then eventually it couldn't have gone below 0. um so like, it had to stop like being negative, right? So that means that y, you eventually wouldn't have been able to find a y which is negative. So like,
Oh, yeah, right.
got it? Like, if this quantity was always negative, then it would give a contradiction, because then you could keep decreasing it, which is false, because it's bounded below by 0. It can't go below 0. Which proves, but here in this case, it is possible for this thing to be positive. On the other hand, this exact same type of property is found here in this quantity, right? Here also we're summing squares, but we're finding the difference and then squaring of vertices separated by another vertex. In this, you'll find the quantity, the difference is such that it will only depend on y. It'll actually be something like the y into the sum. Here is only x plus y plus z, but here it'll be x plus y plus z plus a plus b, something like that. And
Yeah.
yeah, and then you'll see and we know that the sum is positive. So if this will keep decreasing, right? But it's bounded below by 0. It can't keep decreasing. That means that y eventually you will not be able to find the y which is negative.
Oh, right. Yeah.
Did that explain stuff?
Yeah.
So that's the motivation for finding this quantity in particular. Right. Any other questions before we go on? No? Okay. Let's try this question. So you have Okay, so before we go on, extremal principle or whatever, this is just a fancy name. The idea is that when you have like a list of things, a bunch of things, you try to look at what's happening to the maximum number or the minimum number, right? Or the whatever quantity, some maximum, some minimum, and see what's happening. Like you'll often notice some weird and strange things that happen to these things. It's just a general guideline of sorts. It doesn't have any content, but it's just that whenever you have a process, look at um, the maximum of the numbers or the minimum of the numbers, and see what's happening to them. So
So again, bounds might be important here as well.
definitely, bounds are more important. This idea that we've been looking for, that we've been looking at in the previous two questions, where you bound to where you say that a set cannot go beyond a certain bound, and like see you have a max, show that they have a maximum, and then show they're increasing, or show they have a minimum and show it's decreasing. It's a very useful idea. That is indeed useful. Before we
But I
Yeah.
don't get what you mean. Like, what's increasing and what's decreasing?
Right. So let me show using the previous example. Um, Here, the number couldn't go beyond 1,000. Like any row, you couldn't go beyond 1,000. Any column, I mean, like 1, 2, 2, and so on. That couldn't cross 1,000, so that's a maximum. But you
Oh,
also,
right. Yeah.
but you also showed that it's increasing. The number 1, 2, 2, it keeps increasing. It can't decrease.
Oh, okay.
Right. So if you show that there's a maximum and then it increases, you get like very interesting stuff. Like you then it eventually becomes constant because it can't keep on increasing forever, or you get some sort of contradiction because it can't keep increasing forever. Like, did you understand what I'm saying? Yeah, or
Yeah.
definitely, Deeksha. And another idea that I just thought that I'd mention is before, like not 100% related to the extremal principle idea, is guys might have heard the arrows idea, the arrows lemma, or the arrows theorem, or
Yes, Ron also took a class on this.
right, right. So this is like another useful idea when it comes to processes. Whenever like you have a process, like I don't think I'll be doing any questions that specifically involve this. But whenever you have a process, if you're able to show that the process, the set between the process moves, like either the xyz in this case, is a finite set. For example, you can show this by showing x plus y plus z is constant in some process. Then there are only a finite number of x plus y plus z such that that's true, right? If they're positive integers. If the set is finite, um, then eventually the it, the it either repeats in a cycle or it stays constant. Can anybody tell why this is true? The process, yeah.
Wait, what's the arrow thing?
This is the what I'm saying. So if you have a finite set, right? Say x y. Okay, so basically, let me explain that better. So
No,
I'm
I get
saying,
that x plus y plus z is constant, but what do you say? What are you saying? It is repeating.
right? I didn't explain properly. I'm really sorry. So here's what you do. You have a process, okay? You have a process between a finite set. Okay, let's say this represent. Let's use the x plus y plus z is constant example. Let's say it's 4. X plus y z is 4. Then let's say this dot represents 1 comma 2 comma 1, and this represents 4 comma 0 comma 0. Maybe this represents 3 comma 1 comma 0, and you have many dots like that, right? And our process, whatever process we're defining, is such that 1 plus this goes to this goes to this goes to this goes to this, maybe this also goes to this, and so on, right? That's the process. Show that eventually wherever we start, in whatever state we start, say let's say 1 2 comma 2 1, this process will eventually either repeat in a cycle like this, or it will stay constant. This is not like it's trivial, right?
Yes, we can have partition of 5. Like partition of 5 is finite.
Partition of 5.
Yes, we can see that the sum remains 5 only. No, four
Four.
only.
No,
Yes,
that's true. I'm telling you that's true. Like that's
yes.
how we showed that there's finite. But can you show that there's eventually a cycle? The states repeat again and again in a pattern. Like 4, 0, 3, 1, 0, then something, then again comes to 4,
But
0, 0.
what's the operation like? How the 1 to 1 map
Random
to 4 0?
operation. I'm talking very generally. Like don't worry about
Okay, okay.
it. Like can you see why this is true? Like this, like eventually say two numbers. Like there's only a finite number of states, right?
Actually, I can tell why it's
Right,
true.
right. Like
We can prove like after some operation, one will some kth element will be equal to ith element. Then this I will come to cycle till k. Then that k will go
right,
back to
right,
i, and this repeats. Or
right.
No,
either this k
but
just
like,
maps to k k k k k.
but they could repeat in a different order.
They won't. That's the thing because I'm telling you that 4 0 is a process, right? So 4 0 0 0 can only go to 3 1 0.
Oh yeah, yeah.
So
So,
once the same thing comes again, it will go the same way.
but then okay. So okay, suppose it starts with 1 2 1, and then 4 0 0, and then 3 1 0, and suppose 3 1 0 goes back to 4 0 0.
Then
Then
it'll again go in a cycle like this.
yeah, but then it's not a complete cycle because it's also 1 to 1.
But we are only asking for a
Complete cycle.
cycle.
I was saying that it eventually becomes periodic. It repeats.
Oh, okay. So if in the beginning something is left out, it's fine.
Yeah, it eventually becomes periodic. That's it.
Okay.
So again, like you might see, this is not like that. It's like pigeonhole, right? This like it's technically obvious, but it is also sort of powerful
Yes, it is kind of pigeonhole. You are right.
in that intuitive sense. Um, yeah, so this is called the arrows lemma because you can represent the process by arrows. Um, so this is like a useful thing. Like I won't do any questions on it, I think. But like the idea whenever you use this is often like the question will be like show that it eventually is periodic or show that it's eventually constant, and you will have to show that the set is finite, and you often do that by finding an invariant. Because for example, if you show that x plus y is plus z is constant, or if x square plus y square plus z square is constant. By the way, that's a very useful invariant or monovariant or whatever, the summation of the squares of whatever, not only the sum but the summation of squares. Always try that. Yeah, but coming back, like if you show some sort of invariant or monovariant, you can show that the number of states it can reach in the first place is only finite, like it's bounded. And once you show that there's only a finite number of states it can go to, or triples or whatever the case is, it can be some weird configuration too, then you can show that automatically means that it's eventually periodic or constant. Sometimes you can show that it can't be periodic because of some monovariant which keeps on increasing or decreasing, something like that. Being really vague, but you may, if you practice, you'll see questions that use that idea. Right, but coming back to the extremal principle, we'll actually do one question. Right, never mind, we won't. um let's do a very a sort of fun question, I think. Let's say you have 7 dwarves. Um, pardon me if you have seen this question before. And any dwarf, like they're sitting in a circle, and the first dwarf, and all of them have milk, say some amount of milk. Um, the first dwarf takes his or her milk and pours equally in all the other 6 dwarfs, sits down. Then the next dwarf does the same thing, and then next, and so on. And now we're given that after all the 7 dwarfs finish their thing, every single one of them have got back their original quantity of milk. Find how much they had. This is not an Olympiad question, but it's a nice question.
Is it given that how much amount of milk do they give to each other?
How much amount of milk?
No,
They like, can you repeat the question? Like, I just got to know that they are sitting in a circle. After that, what have you said? Can you
Okay,
repeat?
they're sitting in a circle. Each of them have a certain quantity of milk. Then the first one takes his or her milk and pours in every other equally in every other
Also,
person's container.
also,
so i- can I answer?
Yeah, go ahead.
So like So suppose like each person in the beginning, each dwarf in the beginning has 6 parts, okay, like 6x or something, and so they distribute it equally to the 6 people. So like you'll get back, like, so each person will have that much milk, and then you'll get back from 6 people, so you'll get back the same amount of milk.
You're saying that everybody has an equal amount?
Wait, everybody has equal amount in the beginning?
No, that's not given.
Oh,
They can have any amount. As a matter of fact, if they have equal amounts in the end, you'll never have the same. Oh, wait, I don't think I fully repeated the question properly. So the question is that like the first person does that, right? Um, takes his her milk and gives it to all the other dwarfs equally. Then the second person does the same thing.
He
Takes
gives all of his milk or some part of his milk.
all of it equally to everybody else.
Okay.
okay, and so we have to prove that in the end everybody has equal amount of milk.
No, no, no. You're given that in the end, everybody has the same. You're not given. They don't have equal amount of milk. They have the same amount of milk they had before this started.
Oh,
Everybody has the same amount of milk that they had before this all started. You need to show that. You need to find the amount of milks they had. There's no proving here.
So like since this is a question under extremal principle, so maybe we should consider that one person has all the milk and the others have nothing with them.
Not
And
necessarily. Like because that might not be true, right? Like you can easily check that. Like that is not true. Like you can show, like you can assume that somebody has A and then 000, and then you can show that this never turns out to become the same in the end.
and
But
so
what
what if we consider the case that everyone has equal, like the first case that we consider is that everybody has equal amount of.
you can show that that case also never works. If they have equal amounts, in the end they will not get back the same amount. As a
so
matter of fact, you can show that the last dwarf, the last dwarf who does this will have after distribution will have 0, right? So
Yes,
even
he
in the
has to have 0.
yes, even in the first, this dwarf will have 0 milk.
Okay,
it's
so we have some dwarf that has 0 amount of milk.
Yeah,
Oh,
wait, it's given that the initial amount is the same as the final thing, or we have to prove that.
it's given that every single dwarf has the same amount initially as the
So
and after the
we
7
need
dwarf.
to find the amount of milk with respect to the others.
Sure. Yeah.
Wait,
All I
that's
can
what we need to
tell you.
find.
Yeah, exactly. I can also tell you that the total amount of milk is like, I don't know, 5 liters or 7 liters. Say 7 liters.
7 liters.
Yeah.
Okay.
Or you can do it in terms of X. Oh, it's 825. That's sad. By the way, guys, let me send an article if you guys want like more advanced stuff. It has a lot of cool stuff about algorithms of all kinds. Check that out later. We're doing processes, but it has a bunch of cool stuff. So yeah, as someone was saying, this is a question under extremal principle. So what can you do? Like extremal principle sounds obvious when you say it, consider the maximum minimum, but in this case, what can you consider? Okay, for example, can you
Wait,
show?
I
Yep,
think I got it.
go on.
So so let the dwarves be d1, d2, dn, d7. I mean.
Okay.
Okay, so first person first. So d1 distributes it to everyone. So what he gets back will be. Can you write that?
Sure, give me
Yeah.
a
So
second.
he gets 1/6 into okay, summation 1/6 into d 2 to 7 plus d1/6.
Can you say that again? D1.
Yeah, so summation 1 by 6 times the summation is from 2 to 6, 2 to 7, I mean.
Can we declare a quantity Q such that it is equal to the
Yeah.
sum of the milk?
D plus D1 by 6.
1 second.
I
Now
DI.
all of these numbers will keep changing, right? Like, is DI the initial amount?
Yeah, DI is the initial amount for all of them plus D1 by 6. So 1 by 6 into DI plus D1 by 6.
But after the second person has done it, then D3 will have like more.
Oh, yeah. Okay, can you just like tell the solution because we have only like 3 minutes?
It's okay. Don't worry. Try it out. Let's try for 1 more minute. What maximum can you consider, or minimum? This is a question under extreme
I
principle.
think like in the sum remains the constant, and I want to prove that they all try to keep like in.
Okay, wait. Let's do one thing. Here you're getting a problem because you're considering DI to be the initial amount. Let's say we want to fix. Let's say we want to write it just like this. How will what? How will DI be defined then? Guys.
Actually, D1 after 7 sets of moves, he will have 1 by 6 into Q, where Q is constant and sum of all the amount of moves, and Q remains constant always.
Can you say that again? Why is that true?
Like after some 7 moves, like we start with uh, A1, A1's will gets completely uh, distributed. So he gets A2 by 6, A3 by 6, till on to A7 by 6. So after each uh, after like A7 has distributed, he has like Q minus A1 by 6 amount of milk, where A1 is the initial amount of the milk he has.
Okay.
Uh,
So what
1
you
by 6. So I'm thinking like I want to prove that it is kind of decreasing always, and at some point it will have to stop. At after reaching A1, it will like it has to reach A1 sometime.
okay?
But since we are seeing Q by 6 minus A1 by 6, it is repeating like every time. It then becomes A1 of the second one of the, like then it will become Q by 6 minus A1 by 6 minus Q1 minus A1 by 6 by 6. Then this
Right, but
yes.
try to solve the question. Try to get it from that. Um. Okay, so at this point, let me just try uh, tell the solution, I guess. So DI. So this in this thing, instead of defining DI as the amount they had initially, I'll actually define DI as the amount they had while they were distributing. Okay, I'll say that DI is the amount they had while they were distributing. So D1 is the original amount one had, while D2 is the amount after one step because that's when D2 distributes, right? And so this is automatically true. We don't have to subtract stuff or things like that, right? Now let's say, now the thing is we have some sort of average here, right? Now let's say now this average is true for all the other, like D2 can be written as the other six things by six, right? And you can write this like you can write D1 is equal to all the other DI by 6, and D2 is equal to all the other DI by 6, and D3 is equal to all the other DI by 6, and all of them are average. And you
No, but
can
wait, why is one this average of the others?
because like like it gets 1/6 of every person's milk, right?
But
Yeah.
wait, he does not gets. Yes, you are right. Yeah.
Like
then it
I'm
becomes
saying,
unversatile.
D2 is
No,
the
but then if he's getting 1/6 of the other people's milk, it is not their actual original quantity. It's like
correct.
they are also getting
I'm
other
not even
stuff.
thinking about the original quantity.
Okay.
Okay, so the thing is this, d um di. So I'm saying that D1 is the average of the others. Okay. And now I have all the averages, and it's not hard to show here that all of the DI are equal now. But you can also show this using the extremal principle. Consider the maximum DI. That is, we're considering the maximum amount somebody had when they started with the maximum amount a dwarf had when that dwarf was distributing milk. Right? When they were distributing milk, then they can't be the average of all the others, right? Because then the average, they're greater than all the other numbers, so how can they be the average? It's like if a number is, if there you have seven numbers and one number is the average of all the other seven, all the other six, they all have to be equal,
Oh
right?
yeah, yeah.
So what we just showed, every dwarf has the exact same amount when they were while they are distributing. So you can easily make up the sequence. So say first dwarf as x, right? Now this dwarf to the next dwarf who will be distributing gives x by 6, right? So this dwarf must have 5x by 6 because they need to get x when they were
Yeah.
and now the next dwarf has 4x by 6 because they'll get x by 6 from this dwarf and x by 6 from this dwarf, 3x by 6, 2x by 6, x by 6 and 0. Do you guys get this?
Yeah.
We showed something really weird. We showed that they had the same amount while distributing instead of showing how much they had initially. So like it's, you'll often have to consider different quantities, and I probably didn't give enough time for you guys to try this. This was, by the way, this was like a question for 8th graders. Yeah, I'll in some olympiad. Yeah, so seven, right, so I'll repeat that. So did you understand the proof that every dwarf while they were distributing, like before they started distributing, they had the exact same amount? Did you understand that, or should I repeat that?
So like after the okay, so okay, yeah, you should finish first.
Seven week, yes, you understood, or yes, I should repeat? Okay, awesome. So now if they all had the same amount, you can easily make up. So let's say the first dwarf had x, right? Now this dwarf will give x by 6 to everybody else. That means that we want the second dwarf to also have x when the dwarf starts distributing, right? That's what we're saying. Every dwarf has the same amount when they start distributing. So we want the second dwarf to also have x when they start distributing. So that means they must have 5x by 6 because then they get x. And so this one should have 4x by 6 because then they'll have x by 6 from here and x by 6 from here, and so on. Awesome.
Uh, yes, yeah, it makes sense. Actually,
So
intuitively, I
after
wanted
we
to prove this, but actually, I'll somehow lack the intuition to do this.
Okay, nice.
so after we find that like they were having the same amount while distributing, uh, so we just need to like reverse engineer to the initial quantities.
Right.
So that's like so you just need to express it in terms of that x what they had in the beginning, right?
Right. And you can like sum up x, and you can sum up all these quantities and add them up to
Yeah.
7.
So that's it.
Yeah, that's it. We're done.
uh, the article, the handout that you just gave in the chat, it has questions from the USAM. Can we just directly, like, can we just start solving them, or like we need some theoretical background or something like that?
It depends on the individual questions, honestly. There are some some of the questions and the things are extremely difficult. Like I'll be honest with that. Like I didn't take any questions from here, I think. Um, but some of them are like doable. Um, so
Wait,
like
are we doing any more questions or like are
no,
we done?
no, no, no. We're done.
Okay,
Let me
I
actually
need
print
to go
record.
now.
Yeah, please. Yeah.
Bye.
Bye.
It was a nice session.
Thank you.